So thank you, Ilya, for being here today, taking out the time to be here. I would like you to introduce yourself to the audience, talk us through your journey, what you're doing with Hologram, everything.
Well, Kieran, thank you very much for having me. And maybe just before us start, I think what you're doing is a very wonderful endeavor. I think making quantum computing accessible to everyone, which is not an easy topic by itself, is incredible. I think this gives the power directly to the people to research and make new discoveries. And I think your approach is probably one of the best out there, given how curated it is. So thank you very much for all your work, and thank you for having me on.
Thank you
Um,
so much.
but yeah, so very brief introduction about myself. I from very early childhood, I spent a lot of my early days taking things apart. I was always very, very curious. I went through breaking a lot of things, mostly toys initially, and then eventually, basically, I wanted to know how things work. And then eventually, I started to put things back together. So I built computers, I overclocked them, I built drones before they were cool. Um, and I always had this thirst for knowledge, effectively, and how to understand and maybe create new systems. So this, I guess, my journey has led me to this point today, where I am leading two entities. We have an entity called UOR Foundation, which stands for Universal Object Reference. And would love to obviously tell you more about it. Universal Object Reference is the genesis behind a framework that we have built Hologram on. And the
Hmm.
Hologram is effectively an implementation of this new way of seeing and computing information. And the sole purpose of Mission Hologram is to make computing and intelligence abundant and accessible to everyone. So I think in that respect, we're very much aligned in our mission. So I'm happy to tell you more, but maybe I'll let you ask specific questions.
Sure, sure. Thank you so much for that introduction. It's going to be a very interesting podcast. I'm sure for the listeners, it's going to be very new and interesting for all of them. My next question would be, if you could begin with, like in simple terms, explain what hologram is, what fundamental problems are you trying to solve with new geometric computing paradigms?
Sure, sure. I think it's important to take a step back prior to talking about hologram, and I think it's worthwhile me just quickly relaying what Universal Object Reference and
Hmm.
your foundation means and stands for, because
Sure,
it is a
sure.
little bit it is a little bit cryptic.
Hmm.
At the core, we believe that the world around us is informational, first and foremost,
Hmm.
in a sense that physical objects and physics included
Hmm.
emerged from informational field, so to speak. And to that matter, we regard everything as an object. So physical or data is just an object. And UR is effectively a universal coordinate system that maps the address of any object, physical or non-physical,
Hmm.
based on its attributes. Based on its attributes. The world that we live currently, you have a huge amount of systems, file types, and they're all fragmented. They all require interpretation and metadata and pointers for people to interpret. And we feel like that creates a lot of confusion, lack of interoperability, and a lot of waste, time, and energy. So the whole, I guess, vision of universal object reference is that if you're able to address or name the object based on its attributes, then you no longer have to define its type and its location, because the object will be self-describing. And I think a good analogy for that would be, we're effectively packaging any data object into a box, and then the mathematically verified label, which is effectively the proof, is fully descriptive of the object inside, such that you don't have to actually open the box and verify that the contents are there,
Hmm.
or that they're real. You can simply compute and store the proof, which by itself is a much smaller piece of data. And what this enables, it enables a lot of efficiencies. So for example, it removes data duplications, because every data object will have unique deterministic address within this universal substrate. And then anyone who has the address can easily reference and unpack and interact with the object. So that's the basis of our thesis. And from that, you get a lot of benefits, which transcend how we compute, how we store, and how we network information. And I think another point just to note is we feel that data is a lossy abstraction of information, and hence why it has a lot of downstream costs of data management and processing and networking.
Hmm.
And we are trying to basically deal directly with information itself. And we also believe that information has some natural qualities which can be expressed in a geometrical or topological form. So this is now brings us to Hologram. Hologram is basically an implementation of the UR framework, where we are applying this theory, which is no longer theory, by the way, because we have built Hologram, to very fast, energy efficient, and portable computing. And just to stress this computing is completely software defined. So unlike other implementations which are looking to tackle nonlinear computation through hardware, we effectively have created a software defined implementation that is able to virtualize pretty much any type of processing power, whether it's a CPU, GPU, or even quantum circuits. So we can touch upon topological quantum computing, but effectively our software implementation is able to emulate or instantiate quantum-like properties for computing, which we hope to be able to uh, uh, format and package in a way that's easily accessible to everyone. Who, if you're used to working with Docker or Kubernetes, you should have no issues or no learning curve working with Hologram. And that way, effectively, you'll be getting an emulated computing power on the back end that will just plug and play into existing frameworks, whether it's PyTorch or quantum programming languages, which there are many.
Definitely. This is super, super interesting and super unique, and I'm sure the viewers will find so as well. I'll move on to the next question, which is what misconceptions do people usually have when they hear about hologram?
I think hologram is fairly self-descriptive. I think the first thing that comes to one's mind is storage of information using refraction of light. So it's interference patterns of light. I think one thing to stress is that hologram is completely software defined. So unlike quantum implementations that are prone to errors and are obviously very expensive to build, our implementation is entirely defined via software. And I think a good analogy to that is you have posted a wonderful chart of the layers of quantum computing. I believe it's a burger, which is I think is wonderful. And at the very bottom, you have the mathematics, because at the end of the day, mathematics is the universal language that unites all ontologies. And there's obviously different flavors of mathematics. So, for example, category theory is probably one of the most descriptive mathematical languages that unites even other mathematical domains. And then you have exceptional mathematical groups that basically allow you to access and compute within different dimensional layers. So we all know we live in third dimension, but there's a higher dimensions. And so if you make everything computational and you define the mathematical language that is universal and is, let's say, based on a group theory, you have a very powerful computing substrate that's able to express any system from a digital to physical in a computational form. And actually, to that matter, I think our work is kind of similar to the work from Stephen Wolfram. It's they have implementation called the Rulliad, and Rulliad is their take on computational universe, which they use for trying to understand and simulate the reality and physics, biology, quantum sciences. So we have done a lot of research last year, and we have basically defined our own novel mathematical structures. Which is now yielding us this magical like properties. But at the end of the day, magic is just science that has yet to be understood. And I think kind of the truth is in the pudding. So yeah, so I think as I said, the biggest misconception of hologram is that it's physical. But then coming back to my previous point, if you believe that physics emerges from information, maybe it is physical, but just not in the sense that we're used to thinking.
Yes, you've put that very beautifully. And what are some real world use cases where hologram already outperforms conventional infrastructure today?
Sure. So it's a funny one, because if when you create a new mathematical language that allows you to create your own multiverse experience, the first question that you usually get is, what does it do? Or can it make an apple pie? And the funny thing is that by the time you can make an apple pie, you have made the universe that contains the apple pie. So there's definitely at least last year we had a friction of implementation. And given how general and how potentially useful and maybe powerful this implementation is, you can take it in any direction. So as of now, we are focusing primarily on a couple of real world pain points. One of them being energy efficient, ultra fast Bitcoin mining. So this would be, I think a very useful and a very practical application, given that at the moment Bitcoin mining is conducted via specialized ASICs, but it's using traditional maths, which is, it's linear, it's iterative, whereas we're effectively taking the same problems into higher dimensions. And then in theory, we should be able to deploy this on commodity hardware, so CPUs, GPUs, without using ASICs and using a lot less energy. And I think the analogy here is that if you take a knot, physical knot with a rope, and you have two ways of untying it. Either you can fumble in a 3D space, which takes time and energy, or you can take the knot and push it to the higher dimension where things just, they untie and you have more angles to play with. And that's effectively what we do, is we take problems into higher dimensions, we solve them geometrically, and then we bring them back down. So that's one immediate use case. The other real problem that we're solving is the high energy costs of AI computing, which stems from the separation of the processor and memory. So there's a thing called a bus, which basically needs to shuffle data back and forth between processor and DRAM. The processors are really powerful, and most of the time they just wait there to receive the data, and then moving the data back and forth. That's where bulk of this speed and heat comes from. And so the whole idea here is to converge processing and memory into one space, similar to how our brain works. Our brain does in-memory compute, and also combine potentially digital with analog-like behavior, which, by the way, the analog, that's the gateway to quantum-like properties that you can get without having a physical implementation. And I guess the third use case, which I think I'm most excited, to as a touch point with the community, is for us to provide easy to use, ultra performant, and completely free access to emulated quantum circuits, which is instantiated through topological quantum computing entirely in software. So, our intention is to deliver this product to your audience, for them to, build, test, and potentially monetize their inventions and new products.
Definitely, all three very, very impactful areas for sure. Very interesting again. I think I'm going to be saying this over and over again throughout the podcast. But moving on to the next question, how does hologram impact latency sensitivity? Sensitive applications like robotics, autonomous systems, or AR/VR?
Yeah, sure. So this goes back to the point of convergence of data and compute. Um, the biggest problem right now, and also, that also touches the aspect of privacy, where a lot of people don't want to give up their data, so they want to bring models to the data, but that requires expensive compute. So if you can merge data and compute in one space, which is going back to my point of in-memory computing, just like our brains are doing, you're solving these problems pretty much. And so, like right now, for example, local AI inference is very slow for most people, and I would say it's impractical, because unless you have the latest expensive GPU stack cluster, it's not practical, and also you need a lot of memory and so forth. So people are forced to go to the cloud in order to access the performance. But the give up you're giving up here is that it's expensive, and B, you're giving up your data and your sovereignty. And also for edge devices, going to cloud is not an option, simply because decision needs to be made locally. And potentially, I think the solution is a hybrid solution where you have, let's say, a hologram implementation, which virtualizes the GPU. Let's call it a virtual GPU deployed directly on the edge device. And by the way, the hologram, let's say, framework is very, very light. It's tiny. So in theory, you could deploy it even in the smallest space, memory and process space, and that will be able to handle and spin up local models for real time and energy efficient reasoning. And I think energy efficiency is key as well, because obviously for robotics and edge devices, batteries, space and weight is expensive. The other point that we are focusing on is, given that we're using geometrical space for computation, or it's called geometric or symbolic, it's just the same thing. There's also an emergence of a new, I call it, you can call it AI, but it's really not AI, but it's a new reasoning models that are using deductive reasoning as opposed to inductive reasoning. And what it enables basically verification. It enables interpretability, and it's much more energy efficient. So you can have more robust and mathematically verified reasoning models that can also ensure accuracy and trust. And I think this is very important, because for high stakes environments, whether it's medical devices, whether it's self-driving cars, just like our brain, there needs to be an element of predictability
Mhm.
and also, and statistical inference. But the predictability needs to be hard coded, and I think this is where we can come in with our geometrical reasoning implementation. So I think the future is really hybrid. It's combining the existing statistical AI with the new emergent, we call it symbolic or geometrical AI, which is akin to neurosymbolic AI. And in fact, the compute can also be even called neuromorphic compute because, and it's once again, it's all moving towards our mind, how our biology works. So for computing, it's neuromorphic, and then for the cognition, it's neurosymbolic, and then eventually they'll just merge into one thing.
Super interesting. I told you I'm going to say this again. So I I think this is going to cater to a lot of students who are interested in like various fields from blockchain to AI to neuromorphic computing. There's so many people from various backgrounds for sure. Um, Again, moving on to the next question though. How does this change the economics of AI inference and training?
Um, okay, I hope it changes it a lot and for the better and quickly.
Mhm.
That is my intention. And we're working very hard on achieving that. We have plenty of resources. We have a very experienced team. So I think we have quite a high probability of achieving it. As of now, AI training and inference is unsustainable um, on in three dimensions. First of all, it's unsustainable because of economics.
Mhm.
Traditional software has very low fixed costs, and the variable cost is almost zero for distribution. That is not the case for AI products as of today, because the more you use AI for inference, the more you have to pay for compute. And as a result, majority of AI startups are unprofitable. They are, and if you think about it this way, if you're even for OpenAI, if the cost of training a model is increased by, let's say, a factor of, I don't know, 3 or 5x each year, but you're still charging $20 per user. Contribution number one is that we will make AI sustainable economically
Mhm.
by providing affordable and abundant compute, and hopefully it's local compute, which will offload a lot of the demand for cloud. So that's vector number one. Vector number two is um, uh, uh, interpretability. So right now, deployment of AI into enterprise environments um, or, or, or even regulated environments is prohibitive if it cannot be interpreted or explained. And so things like governance, things like ethics, things like compliance, they do not work if you're unable to explain the decision making of the AI model. And I think we're now past the point where AI uh, the pace, the complexity, and the quantity of information produced by AI far exceeds the human ability to process it. So more and more, we're relying on AI both for production and also decision making. And so it's imperative for us to have tools in place as soon as possible to be able to interpret the decision making process. And this is where I think our geometrical canvas will, can enable this because it basically just turns the lights on for the reasoning. And then I think the third dimension of our contribution to hopefully the world is environmental sustainability. I think we all know that the current path for generative AI is not only economically unsustainable, but it's also unsustainable in terms of our energy demands. There's just simply not enough power on this planet for us to render cats all day long. And I think there's a good story of a paperclip factory. If you try to optimize for the largest amount of paper clips, the whole world will be turned into just one paperclip factory, and there'll be nothing left. So we want to avoid that. We also want to make sure that the wider ecosystem is given a voice, given that AI is being made for decision making. And so we foresee application of UR and hopefully hologram to telemetric data for various ecosystems, so forest, animal, ocean data. And the idea there is just to provide a voice for our planet and to collect data and signals to feed into our models, such that we have basically a planet has a seat at the table for decision making. Yeah, so I think that's a very important mission, but that's a bigger goal. And the way we're going to get there is by making other people wealthy and saving them money and time.
Definitely, that's so true. Very great mission that you have, and touching very important points for sure. And my next question would be, what kind of developers and companies should be most excited about building on Hologram, and how easy is it for a developer to migrate their existing workload to your infrastructure?
Yeah, sure. So our North Star is abstraction and simplification.
Hmm.
So given it's software defined, that already makes it a very accessible and very easy to distribute solution because you can deploy it on your existing hardware, whether you're running a Chromebook hopefully you should be able to deploy it on mobile. And this exactly the same implementation or whatever you build with Hologram, it works across all the environments. So if you build something locally, you should be able to deploy it to the cloud and mobile, and then obviously in your work environment eventually, which I think is a very interesting vector. In terms of the so hardware, there's no changes required, which is great. Software-wise, because we sit at such a low level, we effectively can emulate akin to a virtual machine or hypervisor, type 1 hypervisor. We can emulate the compute layer, and then any framework built on top. It seamlessly plugs into us, and it thinks there's a computer there, whether it's a virtual GPU, whether it's a topological quantum circuits. I think on topological quantum circuits, quite interesting because qubit is just a state vector, and the word vector in itself relays geometry. It's a way to represent information in geometrical space. And we're seeing quite a lot of research and development in the topological quantum computing space. It's a very interesting area. You're basically trying to unite two fundamental particles of quantum physics, which are bosons and fermions. And now there's a study that shows there's a third emerging particle called anyon. And through braiding, if you think of how you braid your hair, you can basically build entangled states, which are quantum they're error resistant. They are obviously very versatile and so forth. So that's very, very promising. And I think I'm looking forward to distributing that. But in terms of the users, I think I would hate to say it, but any the big picture is I think it was helpful to anyone. I think the most pressing problems that we're solving is slow AI inference, which I think is a very practical use case. But I think in a more medium term, I think we're seeing emergence of a lot of research and developers who are working with quantum computing technologies in order to future-proof their career and perhaps even to leapfrog their peers, which is especially relevant given the impact AI is having on the developer community, where obviously more and more code is being written by AI. So the question becomes, how do you future-proof yourself, and how do you contribute to the next thing, which we think is quantum. So that's our mission. And as I said, the implementation will require zero hardware changes, and then hopefully zero code changes. So it will be a very similar experience to running a Docker container in your machine locally or in cloud.
Definitely. And how do you see hologram changing AI deployment in developing countries where access to computers is limited?
Yes, exactly. That's exactly the point. We are already working with government of Uganda through United Nations. So emerging markets is a very interesting market because it has a lot of bright people who are hungry to learn and to get access to the emerging technologies. And the best way for them to do so is through leapfrogging. So if you're looking to get ahead, I don't necessarily think you should be looking to get up to speed with the mainstream AI tools simply because they are not sovereign. You're renting them most of the time, both in terms of compute and the data you have to give up. But also you have to look ahead and you have to think of a way to leapfrog into the next level. So I think given how low cost and accessible and accessible and easy to use a solution will be, I really look forward to organic communities forming throughout the world, especially India, where we would have a community of universal object reference, UR, and also hologram that basically becomes part of the framework for learning and building and monetizing quantum applications.
Completely agree. This is so great. Again, I don't want to repeat the same word and say it's super interesting, but it is super interesting and super helpful and impactful. Definitely for sure. And which industries will feel the impact first? What do you think, like in AI, finance, robotics, defense?
Good question. So our intention is to first of all, I mean, the implementation has already been validated internally, so we know that it's functional. We know that it works. We know that it has immense value. The next step is to focus on kind of the lowest hanging fruit application where we can plant our flag in the world to say, look, we're achieving something that previously was considered impossible. And the question is, how is it done? Reason being is because the mathematics behind it is novel. And novelty always comes with complexity and obviously resistance. Uh, now with AI, science is beginning to look a lot like magic. We think that you can turn that magic back into science. Yeah, I think with the right lens, you can turn this magical experience back into science, and this
Mm-hmm.
is how you get progress. And when I say the right lens, is the universal object reference framework provides you this geometrical, universal substrate, what you're going to call it, to map any data object and basically to understand information that you're dealing with. So if you want to explore new horizons and new frontiers across various domains, actually one of the discoveries that we made is that information, regardless of its domain, it has invariant properties. And if you
Mm-hmm.
really want to go to the low level, there's a concept of triality. So the world around us, it naturally slots into the rule of three. It's a very common known phenomena, rule of three.
Mm-hmm.
That's how we tell stories. That's how we process information. That's how nature interacts. And we've also discovered that simple rules, initial rules, can then manifest very complex systems and organisms down the stream through recursion. So the point being is that we're providing them invariant kernel or the initial rules that can then be used to unpack into various domains, but is done on a sequential and deterministic manner, such that you can clearly stop at pause at any point and say, okay, how do we get here, and how does this apply to my domain? So
Mm-hmm.
we're giving you, I think the analogy here for the universal object reference is that we have uh, uh, universe's best library, but without books. You bring your own books, or you can create your own books, but we give you the structure and the index and the way to combine everything together through the invariant properties. Yeah, so I think that's super exciting. And just maybe quickly mentioning the impact on Web3.
Mm-hmm.
I've spent, I didn't touch my background, but I founded a VC fund, which was quite successful in Web3. I've seen it all. I've seen how the sausage is made from every angle.
Mm-hmm.
And I know that the Web3 infrastructure as of today is at its limits in terms of innovation, in terms of application, and it's frustrating for everyone because there's a lot to have been built, but it's not being used, and it's all fragmented, fragmentation of attention, fragmentation of capital, fragmentation of standards. And so our hopefully gift to the world through the universal object reference is ability to map um, uh, every system, including Web2 and Web3, in the same unified geometrical substrate. And that way we can bring everything together. And like just a practical example, at the moment, an NFT is basically an address that lives on a certain chain and that points to another file. And
Mm-hmm.
obviously, there's a lot of complexity there. The file can be corrupted, can be moved. Imagine replacing that arrangement with an address that describes bit by bit the actual NFT, such
Mm-hmm.
that just by knowing what you're looking for, you can find it. And if you were to change a single bit of the NFT, the address will be different. And also the address will be different, not completely different, but it will be semantically similar. So the vector is shifted, which
Mm-hmm.
means that you have a way to apply cognition or interpretation on top, because then you just apply statistical AI for pattern recognition and say, okay, these objects are similar, but they're still different. And so once again, immersive object reference can remap and unite existing Web3 and Web2 systems together into one persistent state, or persistent,
Yes.
sorry, persistent substrate. And that yields immutable storage and compute for the future, because the language is self-descriptive. It doesn't
Mm-hmm.
require someone else to tell you what it means. So the symbols describe themselves based on its attributes.
Mm-hmm. Mm-hmm. Definitely. And I love the library analogy for sure. Um, and how should students and researchers prepare themselves for the shift in computation?
I would say stay curious, stay open-minded. There's a lot of, I think every day now with AI, as I said, if everything feels magical, and there's a lot of noise out there. So my biggest advice is to find high signal sources, whether it's your podcasts or other frameworks, and then follow the signal, follow the high signal sources, and having the right framework, having the right um, resources is imperative, because otherwise your attention will be scattered and
Yes.
you will eventually stumble on the right thing, but you will waste time in the process, and it will be very frustrating. So my biggest advice is find high signal to noise ratio source of information,
Mm-hmm.
um, and then also validate everything for yourself. So if something sounds interesting, learn about it, but also try it and verify it for yourself.
Definitely, that's great advice and very important advice in this day and age for sure. With a lot of misinformation spreading around, that's definitely something to keep in mind for sure. And this is the last question. Any final message you would want to leave with the viewers, young researchers, young developers, about the impact of quantum, about the impact of hologram, about the impact of geometric computing, deep tech, anything?
Yeah, sure. So I think the number one question is why, so going back to my initial point at the beginning of this podcast, when I was small, I grew up in Russia in a place called Vladivostok, which is very, very far from here. Uh, I would break toys every single day. And I think the reason being is because I saw the what and the how, but I wanted to get to the why.
Hmm.
And I wanted to figure out, why is it there? So I think starting with why is very, very important because I think our world is full of what's,
Hmm.
and then people tell you how, sometimes, but not, but they're ready to tell you why. So I
Yeah.
think spending time, really figuring out why you're doing something is very important. And specific to quantum computing, our environment, our nature is a complex system. It's not linear. Linear systems of compute no longer serve us. And we've used all sorts of statistical tricks to try to emulate the complex world around us, but it has reached its upper bounds, its limits. So if you truly want to understand how the world around you works and how maybe even you work, I would strongly suggest to explore, quantum computing, and even how quantum is defined today is very likely to change. So, treat
Hmm.
quantum as a label for now, but don't get too stuck on its current um, definition because it has been also in a dead end for a long time in terms of scientific progress. So I can assure you that how we think about quantum will change quite a lot. So it's a right direction, but don't get too married to the existing structures of it.
Yes, yes, definitely. Great advice there again. Thank you for being here, Ilya. This was a wonderful conversation, very insightful and very interesting, like I said earlier. And I'm sure this is going to like get a lot of students from varieties of backgrounds curious about geometric computing, quantum computing, its applications, all of it, everything that we discussed in the entire podcast is very insightful. And I'm sure people from the business side as well, entrepreneurs, all of them will take something back and it'll be useful in their deep tech endeavor somewhere for sure. So thank you for taking out the time to be here today, Ilya. And I hope we can have another conversation soon, sometime near in the future.
Thank you very much. Thank you for having me.
Thank you. Thank you.